start this. Okay. Only, oh my gosh, come on. It's not reacting. Only one more Friday after this. Do it up. Today, so there was one more example on Newton's law of cooling. I think what I'll do is I'll sneak it in at the top of our notes. But what I want to talk about today is logarithmic scales, which I know you work in, semi-log and log-log graphs. Maybe? Yeah. Okay. I know you work in. Do you? Do you work in those?
Yeah, we did some in Allison's class.
Yeah, she showed me. Yeah, she showed me one of them, and so that's why I thought, okay, that's something that we'll need to talk about. All right, why it works, for example, and when we use it. And so Allison's always talking about, she won't stop talking about order of magnitude, right? So things that that vary greatly in magnitude. Usually the problem that we face is that if we just use a standard scale of measurement, then it gets really kind of bloated and it's hard to see what's going on is usually the problem. For example, if we talk about the distances, is it between, from the sun to the major bodies in our solar system are here. So if we're talking about something like 58 to 4,500, right, there's a huge difference in those values, right? And so that's one of the problems that taking the log is going to solve. Okay? And so if we place these values on a linear scale, everything gets bunched up top here, right? So 58, 108, 150, 228, and then Jupiter, Saturn, and then it gets more spread out, right? And the scale down here is affected by Neptune being so far out, right? And so what we do is we can take the log, yes, the log. We're going to use log base 10, which I'll show you why, but we're going to take the log of these values. And then what we're going to find, or what we'll see, is, so if I take the log of each of the distances, what happens is that, okay, now these are more spread out, or spread out more evenly, I should say, and they're kind of on a more similar scale. Okay, and the reason is because initially these points were exponential, right? And so that's why it works, is because we have this kind of this activity, right? Exponential growth. So then when I take the log of an exponential thing, right, then the log is the inverse of the exponential function. And so now you're back to a linear situation. Okay? And so that's why we do it. That's why we do what we do. Okay. And so let's see here. I just remembered. I have to issue an erratum. I made a mistake last day. Should I do it now? Only one erratum. Errata is plural. Let's see here.
What was?
Pardon? Erratum is an error. Latin, I think. plural, it's errata. It's used in academia where you have to insert your erratum at the end if you made a mistake. So remember this one? And I said, and I feel like I'm off the hook because I was having a really weird day. Did anyone else keep having a weird day? It was like a very weird day the entire day on Wednesday. It's weird. And I was like, well, things are going to be growing continuously, obviously, blah, 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 erratum. So what I want to mention is that we should have used, and I should have not chicken scratched it like that, but I was kind of mad. We should have used this function because, and this is how we'll know for the future, and also reminding myself, unless it says continuous, then you're going to use this function, right? So here my erratum is because, where can I add this? And I'll re-upload the notes. Doesn't say continuous. So we should have used f of x is a times 1 plus r to the x to solve for r. Okay. And so if it's just, well, so that's what threw me off, is that they're always annual rates that we're talking about. And so even the continuous rate is annual, but it's just the flat r, which means that you don't have to divide r by whatever many times it happens per year. It's just a simplified version.
Like there's no like sectional rate.
No, exactly. We only really use that for money problems, like compound interest problems. And so in general, we're only going to talk about annual rates, which is R. Everything else is fine. And what we find is that the rate R, if it's not continuous, right? So if it's just annually, then it's very similar, right? Negative 0.082995957 versus negative 0.0866, blah, 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 right? So they're very similar, and they would be, it's just a matter of how they're growing. Okay? I'll clean this up before I post the notes, but then I'll re-upload the notes from last day. And my apologies.
Yeah, it's not a very good error.
No, it's not. But I feel bad because now it's more confusing to you potentially, which means I have to be nicer. Mostly when I'm marking.
Like beta decaying anyways, constantly, or just like
Well, so that was my reasoning for using the continuous. To me, it makes more sense to use the continuous, and I think it's just a matter of flexing our muscles in terms of using both the functions. And now I'm scared to say anything about the continuous, but I would probably just use the continuous all the time because it's easier to argue, right? Whereas the annual decay rate would be, you only check in every year, right? And in that year, it decays by 8 point whatever %. Right. Not satisfied, but it's okay. Well, I did too. It makes more sense to me, but it's just a matter of practicing, I think. So I'm not too concerned. But just as a note, if it says continuous, then use continuous. If it doesn't, then don't. Feels obvious, but also I screwed it up. So where were we? We took the log of 58, and you can just use your calculator to calculate these, right? But these become nice and breezy numbers. How do we get to 2, for example? 2.03. Well, 1008 or 108, 1008. 108 is roughly 10 to the power of 2, right? 10 to the power of 2. I don't need to use red anymore, right? But I've got is roughly, I'll use approximately 10 to the power of 2, 100, right? And from our knowledge of logs, right, then I have, so 10 to the, or a to the power, or we've been using b, sorry guys. B to the power of x equals a. So 10 to the power of 2 is 108. So then if I take the log base b, and that's why we're going to use 10, is because we're going to be able to rewrite all these things in terms of 10 to the power of whatever, okay, of a is x. Man, that's slow. Okay, b to the power of x is a. There. I always have to do it from this back to here, but usually we want to start here and go here. So I need to work on my speed, right? And so now I have 10 to the power of 2-ish, right, is 108. So then if I take the log base 10 of 108, well, that's going to be roughly 2. Right. So here, notice or first I'm gonna write those out bigger because that wasn't very nice. It's all crammed up there. Recall, if b is to the power of b to the power of x is a, then log base b of a is equal to x. If we let b be 10, then we're working in base 10. We can rewrite 108, and I'll make a note here, Venus 108 is roughly 10 to the power of 2. So now if I map this to the log, right? So therefore the log, and I'm going to emphasize the 10, but only once, because we know that. Log base 10 of 108 is roughly 2. Notice what's happened here is you're going to go from this power, right? And that's going to be your log result approximately. Okay? And so that's how we get to these values. You can use your calculator, right? But if you have these in terms of 10 to the power of whatever, then you can convert them that way. And so that's why it works. Yes. And this is the benefit. Right now we're on this kind of stretched out, linearized scale, right, where they're not all scrunched up. And so here, this is what we would call a linear scale, right? So we take the log to linearize things. Okay? And that's tracing back to my realm, statistics, right? Where if I have something that follows some sort of exponential distribution, usually what I do, or a trick of the trade, is to take the log and then it turns it into a straight line, and straight lines are a lot easier to model. The problem is interpretation, then you have to unlog it, right, to get it back, or take the exponent, but that's okay because it's going to be a lot easier to model. So that's what I want to show you today. Got very slow iPad, which I can't seem to fix. Oh yeah. Yikes. Did I warn you that it was going to be all morbid? There. So that's the one I'm going to add. And we're not going to do this one, but let's do this one. It better have copied. There. What value does the point plotted on each log scale correspond to? So now here we have the log of x is 3.25. And so here we're told that the log base 10 of x is 3.25. I can figure out what point that is by taking 10 to the power of 3.25. Therefore, x is 10 to the power of 3.25. I'm gonna need my trusty calculator. 10 to the power of 3.25. So I get x is 1778.27941. Squeeze it on. How about this little guy? Looks like between 10 to the negative 1 and 10 to the negative 3. 10 to the negative 3 means that, so if I have 10 to the negative 3 is equal to x, I can take log base 10. So then the log of, we'll go nice and slow, still pretty early, 10 to the negative 3 is the log of x, which means if this is log base 10, which it is, then that's going to cancel with the base of 10. Yeah. Oh my gosh. Yep. No erratum needed, just under the radar 1.5. Sorry about that. There. Bless you. Thank you. That would have been confusing. Where did the negative 3 come from? Or did you just know that I was wrong and you rolled with it?
I can just barely see those numbers.
Oh, that's fair. It's all part of it. Convince you. Yeah. Yeah. I know. So now log base 10 of 10 to the power of something is just going to be whatever is in the power, right? Because that's the log laws, right? So then negative 1.5 is the log of x. And I think that's what we wanted to. I'm happy with that. Oh. Nice. Now, where am I going next? In here. So you can try it. But when we talk about orders of magnitude, what we mean is the log of A over the log of B. And there's an example here. But I already copied, so I shan't. Makes me want to restart my iPad. So if we have two values, A and B, when we talk about their order of magnitude, right, which, like I said, I've heard Allison say a bunch of times. So I know it's a thing that you have to deal with. And so what it means is, okay, so if I have A is, let's say, 10,000, right? And let's let B be, I don't know, 100. Then we could rewrite 10,000, 10,000, is 10 to the power of 1, 2, 3. Oh shoot, 1, 2, 3, 4. 10 to the power of 4. Phew. And B is going to be 10 to the power of 2. I only do that because it's easier to do, especially if you don't have a calculator, right? But you will. So then the difference in the order of magnitude is going to be the log of A over B. So the reason I rewrote them in terms of powers of 10 is because we're going to have the log of 10 to the 4 divided by 10 to the 2, which I can simplify by bringing this 10 to the 2 upstairs by rewriting it as 10 to the negative 2, right? Or if you prefer, you can just cancel, but technically that's what you're doing, right? And so this becomes the log of 10 to the 2, right? 4 minus 2. If I take the log base 10 of 10 to the power of 2, this just becomes 2 from our log laws. So then the difference in order of magnitude between 10,000 and 100, let me put a little comma there, it's easier to read, right? 10,000 and 100 is going to be 2. So that's how that works. Okay. Scared to. I wish you could see how many times I'm pressing stuff. Maybe that's the problem. I'm too impatient. So one of the scales that we're going to talk about is the moment magnitude scale, which I guess is very similar to the Richter scale, except it uses something else. So similar, but not. So for an earthquake with seismic moment S, right? So here's your S, a measurement of earth movement. So that's what it measures instead of, I don't know what the Richter scale measures. The MMS value or magnitude of the earthquake is 2/3 times the log of S over S0 or S naught, if you're like me, where S naught is 10 to the 16. Which is a baseline measure for the seismic moment. Okay. So this S0 is always going to be 10 to the 16, but usually we can get away with not plugging it in and just talking about relative to the baseline, right? How big was this quake that we saw? Okay. And I'm scared to go grab the examples. I'm going to see if I can grab both at the same time. Let's see. I'll put this one on the same copy. That way I only have to come back here once. Copy. Really testing my patience. Oh my gosh. This is insane. And I'll put the other one in here just so I don't lose it. So one earthquake has an MMS of magnitude 5, and a second one has magnitude 8. How much more energy was there in the second earthquake? So remember, S is the energy, the seismic moment. And so what we're given is that we have, if I write down formula, M is 2/3 times the log of S over S naught, or S0 if you prefer, where S0 is 10 to the 16. I'm actually gonna leave that out so that I don't make a mess for a little bit longer. So we're given that one has a magnitude of 5 is 2/3 times the log of S over S0. Trying to solve for S for this first earthquake. So I have to multiply by 3 and divide by 2 over here. So I get 15/2. I'll write it out though. 5 times 3/2 is the log of S over S0. over 2 is the log of S over S0. I guess I could do 7.5. Sure. There. Now, if I'm trying to solve for something inside the log, then I have to look at the base of that log, which is 10, and I'm going to take both sides and raise them to 10. So 10 to the 7.5 is 10 to the log of s over s0. 10 to the 7.5 is going to stay. Oops. But the s over s0, oh, clean that up. What I can do is I can multiply this baseline energy right over here, and I can say that, okay, in this case, S was 10 to the 7.5 times S0. Right? Which is really saying 10 to the 7.5 times the baseline. I'll say earthquake 1, earthquake 2. Had a magnitude of 8. Same thing. 2 over 3 times the log of S over S0. Oops. 8 times 3 divided by 2 is 12. Skipping some steps, that's okay. Is the log of S over S0. So now again, 10 to the power of 12 is S over S0, which means that S in this case, we were expecting it to be larger. In fact, it's 10 to the 12 times the baseline, right? Which is larger than the magnitude of 5, right? Which was 10.7 or 10 to the 7.5 times the baseline. So here, 10 to the 12 times the baseline. Now, in terms of the order of magnitude, let's see here. Or maybe I'll say the difference in order of magnitude is going to be the log of, let's say, S5. Doesn't really matter. I'll do the bigger one on top, just for cleaner numbers. S8 over S5. And I'll denote here, this is S5 and this is S8. Usually if I've solved for the same thing, but for different groups, I just put little subscripts on, just like that. So now this is the same as the log of 10 to the 12 times S0 divided by 10 to the 7.5 times S0. So this is part of the reason why I kept it just as S0, so I don't have to simplify it. Although there's no harm in putting in the 10 to the 16, right? But in this case, I can just cancel it and I can focus on the 10 to the 12 and the 10 to the 7.5. So now this becomes the log of 10 to the 12 minus 7.5, which is 4.5. The log base 10 of 10 to the power of 4.5 is 4.5. which means that there was 4.5 times more energy in the second earthquake. Therefore, the second earthquake had 4.5 times more energy than the first. Yeah.
Is there like an order of magnitude?
I didn't see any. That doesn't mean it doesn't exist. I just don't know about them.
I'm
Yeah. For now, my answer is no. But that feels like maybe a wet question. So I don't know. I don't know. I feel like we just say order of magnitude. But this one, only because I'm running out of time. Okay, I'll put this one here and I'll add the solutions before I post the notes. But it's similar, right? So one earthquake has a magnitude of 3 and a second quake has 10 times as much energy as the first, which means you have to find how much energy was in the first and then convert that to the magnitude, the MMS magnitude, right? So it's just another way of working with this function. But what I want to show you is, now let's see here, is the log, or the first we'll do the semi-log graph. Which is basically half of a log-log graph, which I think is what you are using more, right? And so is the log-log, not just the semi-log, although it depends on what you want. Oh my gosh. Okay, so we are doing 4.7, just briefly copy, but I'm gonna scroll down here. So what happens is usually we have graphs like this, which are clearly exponential, at least for some portion of the graph. And so here we have stock something or others, and from 1928 to 2010, like took a crash here, you know that. And so usually what we do is we transform these on a log scale, and notice, so this is what you're familiar with, is when your paper does the work for you of doing the logs. And so you could have just graphed it on you know, in Excel or whatever and taken the log of the output and you'd get the same thing. But the log paper, it just changes the scale so that you're not on a linear scale anymore, but you're on a log scale on the y-axis. Okay. And so both of these have a linear scale, meaning that the space between them is the same on the x-axis, whereas a log-log graph has the log on both axes, and that's the difference. So that's why it's more condensed, I don't know, in one of the corners, can't think straight, as well as on the y-axis, I guess in the outer corner. Sure. No. Gonna do something weird so that we don't have to. this garbage. So a semi-log graph, right, is one with one axis, or I underlined the wrong, one axis using a linear scale and one axis using a logarithmic scale. So semi-log would look like this. You've got the log of y and x, whereas a log has the log of y and the log of x. How do you know when to take the log? We take the log if the values are showing exponential behavior. We take the log if the values of x and or y, usually it's the y, so maybe I'll swap these, because usually it's the y that we start with. Show exponential behavior. For example, if f of x is a times b to the x. Seen that? Right, so if you can model those values with that, a times b to the x, then when we take the log of this, the log of f of x, or the log of y if you prefer, right? Whenever you see f of x, you can just read y if that makes more sense to you. And so this is going to be the log of a times b to the x. Now there's where the power of the log laws come in, is because now I have a times b to the power of x, and I'm multiplying inside the log, which is the same as saying the log of a plus the log of b to the x. Cool. Then what? Then I have the log of b to the x, but that's the same as saying x times the log of b. And so now I have the log of a plus x times the log of b. The log of a is just a number, right? The log of b is just a number. So now, right, if I use, so here, this is a number and this is a number. If I ignore those and just call them some constants, I don't want to use, I can use mx plus b, but it gets confusing because we had a b in there, right? And so a plus bx, that doesn't work either. What if I use, what can I use? Was there a suggestion? I'll use the stats notation. B0 is the intercept plus B1 x, where B0 is the intercept and B1 is the slope. As long as you recognize that there's just a number on its own, and whatever that is the intercept, and then x times a number, well, that number has to be the slope then. So now, right, we have this linear function, which we know how it behaves, right? I can draw this line, and we can do a bunch of fun things with it. right? And it's easy to grasp. Okay? And so that's the benefit of taking the log. And here I'll just write, in this case, recall f of x is y, right? So if you want to replace those f of x's with y, then that's fine. The reason I mention that is because that's what I have up here, the log of y, the log of y, right? And so now I've transformed these, and now they're going to be a linear function, which I can fit a straight line to, and we could use linear regression if we wanted to. And I think I don't have time today to do that. But I was playing around in Desmos, and Desmos can fit linear regression. So I'll get that set up. Just sign up for an account. Get that set up for, yeah, I know. Darn it. I made it for so long. But pretty neat. Any questions? Well, oh, yes. More? Is it this one? Yeah, we take the log if the values of y and or x. And or x. Made a mess. I'll clean that up. And or x. Okay. There. Now there truly is only one more Friday left. Did it. If you have any questions, let me know. But we'll keep looking at these graphs on Monday. Oh, stop this.